All right, guys, today we're going to talk about how to go about a parallel circuit. And first of all, what is it? All right, so getting into it. A parallel circuit is a circuit in which there is more than one path for the current to flow. So in a series circuit, we know that there is only one place the current can flow, and that is just around the circuit. Okay, so here's an example of a series circuit. Current can only flow in one path through both resistors. In a parallel circuit, things are a little bit different because now we have multiple paths that the current can flow. So in this case, the current will begin here, but it's going to reach this junction point in which you can either go down to this first resistor or you can keep going around to the second resistor. Okay, so that would be an example of how there's more than one path for the current to flow. In the case of this parallel circuit, if one element is burnt out, doesn't matter because you still have another path that the current can flow. So it's not required like the series circuit where if one goes away, the whole thing doesn't work. In this case, most of the time it's going to continue to work. When you're looking at, when we're doing calculations, for example, as you get further to the right, you're going to add numbers. So this first resistor is the first resistor that we hit. This will be the second resistor, and then keep going, that's your third resistor. So when you're doing your table, you're going to number them from left to right. Okay? All right, so the rules for for a parallel circuit are a little bit different. Because current can flow in multiple paths, you now have to think about, okay, how does that determine my total? So let's kind of draw it here. So let's say I've got a total of 2 resistors here. So for my total current, I'm going to think about it's the current that flows through each branch of our circuit. So this would be the current flowing through the first branch plus the current through the second branch. And then for however many other branches you have, you would go from there. A little bit different, potential difference is going to be the same across all of them because you have the same beginning and ending points. You start with all your voltage here before the resistor, and you have no voltage left at the end of your resistor. So, like we did for current for series circuit, the voltage drop across each resistor is going to be exactly the same value. So in your table, you could just straight across, you have the value. The last piece is resistance. This is a little bit strange. You see there in the formula it listed as this like fractional shenanigans. I'm going to kind of write it in a different way to sort of help you with your calculations. So you don't have to worry about what's the last step. So I think of it this way. The total resistance is really looking at the different resistors, and you're doing fractions of each resistance. So I think about the value of the first resistor I'm going to place in the denominator. I'm going to add it to the value of the second resistor, but the resistor is in the denominator, okay? And then however many you would have from there. The last step, once you add those fractions together, you're going to take the inverse value of that total, and that's going to give you your total resistance for your circuit. Fun fact, I wanted to make sure that you're aware of this. The value for each resistor is always going to be larger than your total resistance, which doesn't make any sense. In the series circuit, it's the complete reverse, right? Your total resistance is the largest value. But in this case, it's strange. It's going to be the smallest number. So if you get a total resistance that is larger than either resistor, you've done some kind of funky math there because it shouldn't be that way. All right, so let's get to an example. I'm going to go to the second one. Okay, so you see there, that is our circuit. What I'm going to do is I'm going to write a big version of our table just to kind of help us with calculations. So we always do the voltage is equal to the resistance the current multiplied by the resistance. The first thing I list there is going to be my total. In this case, I have 2 resistors, 1 and 2. So I'm only going to list that there. Okay? So from here, let's kind of put our equals and all that we know from what we just talked about. So your total voltage, the voltage drop across each resistor is going to be exactly the same. So whatever you have as your total voltage, you're just going to bring that number all the way across. Okay? Your total current, however, is going to be slightly different. It is the current that travels through the first branch plus the current that travels through the second branch. Because remember, since it has multiple paths it can travel, you may have different amounts. Okay, so it would be this first current pathway plus the second current pathway is going to give you that total. Okay, this last one is a little bit more challenging to write. As a reminder, it's going to be your total resistance is going to be, I'm going to sort of write it like this. I've got this 1 over whatever my resistance is plus 1 over whatever that resistance was. And then I'm going to put that all in parentheses and put that to the inverse. Okay, so to the -1 power. That's how I'd write it, but know that when you determine your resistance's values, it's just whatever the number is. This is just to determine your total resistance. Okay, so let's plug in some values. According to our circuit here, the total voltage according to that battery is going to be 6 volts. So I'm going to list that there first. And then it gave you the information of the current, how much travels through the first branch. That first branch is going to have 2 amps of current. The second branch is going to have 1 amp of current. Okay, so from here now we kind of go with our puzzle like we talked about before. The first thing I could probably go ahead and do is, knowing that I have my total voltage, I'm going to go ahead and list the total or the voltage for each branch. So we know that each of them is going to be the same exact value. Okay, I have 2 different options here. I could go ahead and find the resistance values for each of these items, or I could go ahead and find the total current. Doesn't matter which, your choice. So let's go ahead and do the current first. Okay, so I know that I've got 1 amp of current. I'm going to add that to the 2 amps of current going through each branch. So the total current that I have in my particular circuit is going to be 3 amps. Okay, you're probably already seeing what you can do here. You can go ahead and find your total resistance without even having to do the whole you know, fractional inverse situation, but I want to be able to show you both options. So we know that V is equal to I times R, so 3 times something is going to give us 6. We know that would need to be 2 ohms. Okay, but I'll show you in just a second what that looks like to do with this whole formula as well. So I can find the resistance for each of these two using the same situation. So 6 equals 2 times something. That something is going to be 3. So 3 times 2 is going to give us the total voltage, which was 6. In this case, I've got the same thing. V equals I times R. So 1 times something gives me 6. That something would be 6 ohms. Okay, so let's go ahead and look. You can see there the total resistance is smaller than both the 3 and the 6. This makes sense. This should work. So if I go ahead and plug it in, if I were to find the total resistance using just the information here in my fractions, I've got 1/3 plus 1/6. The last step would be to find the inverse of that. So if I plug that into my calculator, 1/3, oops, let's try that again, 1/3 plus 1/6. Now I'm going to take that all to the -1 power, and there you have it. The value is 2. Okay. Fun fact, you cannot add your denominators together to get a value. That's just basic math. Just wanted to remind you of that you would have to make sure that you're adding you know, you could find a common denominator and go from there, but, you know, the calculator pretty much does it for you. But just as a reminder, you could not add and say I have 1/9 and then take the inverse of that. That is not correct. Okay, and by using our rules, right, we know that the total resistance should be the smallest value. If you got 9, you obviously know something is up because that's bigger than both 3 and 6. Okay, hopefully this was helpful to you. Thanks, guys.